What's up, Cal Gang? Welcome back to some dynamics. So let's solve this problem. So we have a chord, and it's pulling with an acceleration of 10t meters per second squared, and it's starting from rest. And as you can see, that chord is pulling tangent to this circle, which is spinning around this origin. So we want to find the angular displacement, angular velocity, and angular acceleration at 3 seconds after it's being pulled. So let's go ahead and solve for that. So angular acceleration relates to tangential acceleration like this. Acceleration tangential is equal to angular acceleration times the radius of the circle. So we're pretty much given all this information. So first of all, let's solve for angular acceleration. I know it's last, but let's solve for it first. We can divide by r to get the acceleration tangent over radius. Now this acceleration that we're giving to the circle is always tangent, right? It's not even it's pulling only in the tangent direction, because if we were to draw an axis, this would be tangent and this would be normal. So it's always in the tangent direction. So we can plug in what we know acceleration tangent 10t for this. So we're going to get 10t over radius, which is 0.5. So we're going to find that an angular acceleration is equal to 20t. So now we can find at 3 seconds by plugging in 3. So we're going to plug in angular acceleration in 3 is equal to 20 times 3. And we're going to find that angular acceleration at 3 is equal to 60 radians a second squared. Okay, cool. So now let's go ahead and solve angular velocity. So similarly to how velocity is in the integral of acceleration, angular velocity is also the integral of angular acceleration. So let's solve for that. So angular velocity is equal to the integral, and let's use the bounds 0 to 3 seconds, just so we don't even have to solve. Right? Or let's not do that. Let's not put in bounds yet. Why not? Okay, so then we're going to put in our angular 20t dt. So then we're going to solve this integral, and that's going to become 10t squared. And then if we add a plus c, right? But we know our initial angular velocity is 0, so we're going to find that c is equal to 0, and it's just going to become this. So if we want to find it at 3 seconds, we're simply going to plug in 3, so it's going to become 10 times 3 squared. And we're going to find that angular velocity at 3 seconds is equal to 90 radians a second. Nice. So then all we have to do left is solve for angular displacement. So this is theta, right? This is the integral of angular velocity. So we can do 10 t squared dt. And then this time, because we don't really care about this equation, we just are concerned with the number, we can set our bounds to be 0 to 3. So then we're going to find this is 10 over 3 cubed, right? Because this is going to come down, it's going to be bounded from 0 to 3, the 0 is going to cancel. So this 3 is going to cancel with that 3, and it's going to be the same as 10 3 squared, which is the same as what we found here. So we can find that our angular displacement at 3 seconds is 90 radians. And there we go, we solved the problem. Right, so super easy question, just about making sure kind of you understand the concept. So if you're still struggling, feel free to check out the rest of my channel. I have a whole lot of more problems on chapter 16 moving forward. So thanks for your support, thanks for watching. I'll see you in the next video. Peace.